we're going to solve quadratic inequalities, starting with the product of x minus 1 and x plus 1 less than 0. We want to find out what values of x make that occur. So I'm going to set the left-hand side of this expression equal to y, and notice that if I multiply it out, I actually get y equals x squared minus 1. And we know what that graph will look like. It will be a parabola, the same as y equals x squared, moved down 1 vertically. And we'll have x-intercepts plus and minus 1, looking at those original factors. And we are going to compare the graph of y equals x squared minus 1 with y equals 0. Actually, we're going to compare the y values. And we want to know where the y values in y equals x squared minus 1 are smaller than y equals 0. So that's going to be the values between the x-intercepts. And so here the values of x are going to be in the open interval from -1 to 1. And the graph on the x-axis on the number line will go from -1 to 1 with open circles at both -1 and 1 and a solid segment between the two. So our knowledge of quadratic functions and their graphs is very helpful here. In the second example, we'll be interested in the function x times 2x plus 3. So that'll be y equals 2x squared plus 3x. We notice that the x-intercepts are x equals 0 and x equals -3/2, looking at the factored form. Again, the parabola has leading coefficient which is positive, so opens up. This time it passes through -3/2 and 0. And we are looking for where is this graph greater than or equal to 0. And so it is going to be on the outside of the x-intercepts of the parabola. This is y equals 0, and this is y equals 2x squared plus 3x. And so this time the intercepts are included because it's greater than or equal to. And so our interval, we're going to have two intervals here with a union. So it's going to be from -∞ to -3/2, including the -3/2, union 0 to infinity, including the 0. When we draw it on the number line, we'll have closed circles at -3/2 and 0, and a segment between those. Our third example is x squared minus 3x minus 40 less than or equal to 0. And the leading coefficient is 1, so the graph of y equals x squared minus 3x minus 40 will be a parabola opening up, and we'll want to know this time where the y values are less than or equal to 0, so where the parabola is below or on the x-axis. This time we'll see that the function does have two x-intercepts since it factors as x minus 8 times x plus 5. And so the x-intercepts this time are going to be 8 and -5. You can already probably visualize what our solution is going to be, because here is y equals 0, here is y equals x squared minus 3x minus 40. And we're looking for where the y values are on or below the x-axis. And so our solution will be the closed interval from -5 to 8. And on the number line, we'll plot -5 and 8 with closed circles and join them with a line segment. One last example. 5x squared plus 13x greater than or equal to 3x squared plus 24. In order to find the x values that satisfy this, we could in fact look at two separate functions, two separate quadratic functions from the left and right sides. But it is much easier if we set one side equal to 0 by subtracting 3x squared plus 24 from both sides. This results in a new quadratic function, and this function does not factor, but let's see if it has any x-intercepts by using the quadratic formula. X would equal the opposite of 13 plus or minus the square root of 13 squared, which is 169, minus 4 times 2 times -24, which I believe is plus 192, all over 2 times a, which is 4. This gives us -13 plus or minus the square root of 361 all over 4. -13 plus or minus 19 is the square root of 361 over 4. This gives us 6/4 and -32/4, or 3/2 and -8. And so when we draw our parabola here, we're going to have -8 and 3/2. It's going to open up because the leading coefficient is positive. And we're looking for where the graph is on or above the x-axis, because we have the function greater than or equal to 0. So we'll have outside the x-intercepts. So this will be the interval from -∞ to -8, this time including the -8, union the interval from 3/2 to infinity, including the 3/2. On the number line, we locate the two values with closed circles and join them with a segment. And there is an alternate way to proceed if you don't want to draw the graph of the function, and that's called using the sign chart. And with the sign chart, once we determined what the factor or what the zeros were for the function, we would actually factor that function and since its leading coefficient is 2, we would include that factor. It would be x minus a -2, which would be, or 8, which would be x plus 8 times x. And I'm sorry, I put a -3/2 on this number, on the number line. It should have been a positive 3/2. So x minus 3/2. And then we would draw our number line again and put the factors x plus 8 and x minus 3/2 here. And realize that x plus 8 is going to be positive when x is greater than -8. So we put positive signs in these two sections and negatives to the left of -8. We also realize that x minus 3/2 will be positive to the right of 3/2 and negative to the left of 3/2. And so when we do the product, we see that to the left of -8, we have negative times negative, which is positive. In the middle, negative times positive, which is negative. And to the right, positive times positive, which is positive. And so we want the two intervals that are on the outside because we want to know where the function is greater than or equal to 0. You're welcome to use a sign chart if you prefer.